This is video 4 in the topic, How do musical instruments make sounds? In this video you're going to be looking at harmonics in the human voice. This is presented by your guest lecturer, Professor Joe Wolfe.
Physicists like to discuss sine waves, which are in a strong sense the simplest type of travelling wave. Let's take a snapshot of a sine wave. Let's take a look at the displacement as a function of position at an instant in time. The distance between two adjacent crests is called the wavelength. And I'm sorry for the Greek letter, but that's universally given the Greek symbol lambda. So, if we look at a wave travelling to the right and we look at displacement at a particular point over time, we see that a particle oscillates up and down in a sinusoidal motion. We can also see that for one cycle of that up-down motion, the wave progresses a distance lambda in the direction of its propagation. So let's call the time of one cycle capital T, the period of the vibration of points on the wave, wavelength lambda. The distance travelled in time t is one wavelength lambda, and the period t is the reciprocal of the frequency. Therefore the wave speed v is lambda over t, which is equal to lambda times f. Let's now look at the reflection of a sine wave at a fixed end. Here's the wave machine with a sine wave travelling along meeting the fixed end. In the cartoon, we can also show the inverted wave appearing magically from beyond the fixed end. What we notice is that for a little while the wave is simultaneously travelling to the right and its inversion is travelling to the left, we have a standing wave, a wave in which the pattern is not going anywhere. Notice that there are points in the standing wave where there are no motion and points between them where the motion is a maximum. What sort of wavelengths can produce standing waves on a string? Well, if there's only one fixed end, then any wavelength can lead to a standing wave. If we have two fixed ends, we limit the allowed wavelengths. Let's look at a musical instrument. It's tempting to say fixed end at the nut and fixed end at the bridge. This, of course, is only an approximation. The whole point of the box of the guitar here is that a vibrating string causes a tiny vibration in the bridge. That causes a vibration in the belly of the guitar and also to the air contained inside the body of the guitar. And that's how the sound gets from the vibration of the string, vibration of the bridge, vibration of the belly, out into the vibration of the air in the sound wave produced by the instrument. But let's make the very good approximation that the string is fixed at this end and at that end. An infinitely long medium can support standing waves of any wavelength. Strings, however, are fixed at both ends. If we call the vibrating length L, then L must fit exactly n half wavelengths where n is an integer. The string can therefore resonate at a set of discrete wavelengths, lambda n equals 2L over n. We know how the wave speed v in a uniform string depends on the tension T and the mass per unit length mu. The frequency is the wave speed divided by the wavelength, so we can write this expression for the set of resonant frequencies. The animation shows some of these resonant standing waves, which we call modes of vibration. Their frequencies are called the harmonic series, for reasons that we'll hear later. We can see this in a rope where the vibrations are slow enough to see. I keep the tension constant and excite the wave with different frequencies, and I see that there are standing waves here with a frequency F1, with twice that frequency, with 3 times that frequency, and with 4 times that frequency. All of these standing waves are what we call resonances of the string. A resonance is the capacity of some system to store energy at a particular frequency. This string can store mechanical energy at a frequency F1, or at 2F1, or at 3F1, 4F1, so forth. Well, these frequencies are nice to see, but they're too slow to hear. So instead, let's go back to thinner, lighter strings on a musical instrument. I pluck this string and can excite most of the modes having displacement nodes at the ends. The common factor is F1, which determines the pitch we hear and which we call the fundamental. We can increase the frequency if we increase the tension or decrease the vibrating length or decrease the mass per unit length, which means using different strings. We can also change the pitch by suppressing some of the modes. I've tuned this string to C3, that's the C below middle C. If I touch the string very lightly, halfway along, I suppress the first, the third, and all odd-numbered harmonics. Now, the highest common factor is 2F1, which determines the pitch. This is an octave higher than F1, our fundamental. 1/3 of the way along, the common factor of allowed modes is 3F1, a musical 12th above the fundamental. And so on for the rest of the harmonic series. From these we can play the tunes that bugles play. That harmonic series of frequencies is very important. Let's plot them. Here is the lowest frequency, which I'll call the fundamental at frequency F1. Let's now consider the second resonance, the second in the harmonic series at 2F1, and I'll add it to the first. Now I'll add 3 times that frequency, 3F1, and 4 times that frequency, 4F1. If you look at the sum of those waves, you'll see that after one complete cycle of the first vibration, we've got 2 complete cycles of the second, 3 complete cycles of the third, and so forth, so that the whole series is ready to start again. If I only have frequencies F1 plus 2F1 plus 3F1, etc., if they're the only frequencies present, then after one cycle of the lowest frequency, the whole sequence starts over again. That's an important part of Fourier's theorem. It tells us that the sum of vibrations in the harmonic series is a periodic vibration, a vibration that is repeated in time. The converse of that is also true, but it's rather harder to show. It's also true that periodic oscillations can always be written down as a sum of members of the harmonic series, F1, 2F1, 3F1, and so forth. Many important sounds in the voice with musical instruments are exactly or almost exactly periodic and therefore are made up of a harmonic series of vibrations. Examples, the voice and most musical instruments. Why should they be periodic? Well, if we consider the parameters that produce the vibration, the stiffness of a vibrating reed, the air pressure that's driving it, or the tension in the vocal folds and the air pressure that are driving those. If I keep the physical parameters of a vibrating system constant, then I'd expect that one vibration would be very much like the next. So if the vibrations are repeated in time, then we get a periodic vibration, and thus a wave that can be written as the sum of frequencies from the harmonic series, as the sum of harmonics. Examples of that: vibration of the vocal folds, ah, the vibration of a reed at constant pitch, and the bow string interaction on a bowed string instrument like a violin. Repeated cycles, therefore periodic vibration, therefore the harmonic series. We can analyze their sounds as the sum of harmonics. So for instance, if I sing a low A, ah, at 110 Hertz, its fundamental is at 110 cycles per second. The next harmonic is 220, then 330, 440, etc. My voice, singing ah, can be written as a sum of all of these different members of the harmonic series, which stand out clearly in the spectrum of the voice. The spectrum is a plot of the amount of each frequency that's present in the sound. Strictly, I should also show you the phase of those vibrations, but I'll leave them out for this lecture. So let's have a comparison between ah and ooh, two different sounds, different timbres with the same pitch, but with different proportions of the different harmonics. Ah, ooh. We can also look at the different proportions of the harmonics present in different musical instruments. Here's an example taken from Fizz Clips. Notice that the spectra of those different sounds are rather different, but you'll also notice that the time variation, the way in which the amplitude changes over time, is very different too. Both of those things, the way in which the amplitude varies in time and the different harmonics present, are important to determining the timbre of a note. So, periodic waves can be written as the sum of harmonics, which makes harmonics very important in music. We might also think that harmonics have got to do with harmony, and that's actually true in an important sense. Universally in human music, the octave is considered a very special interval and often called the most harmonious. So here's an example of the octave. Remember, doubling the frequency. Ah, ah, 110 Hertz, 220 Hertz. If we look at the spectra of those, we see that our first one has got 110, 220, 330, 440 and so forth. The second one, 220, 440, 660, so forth. In other words, the harmonics of the octave higher are a subset of the harmonics of the lower note. Ah, ah. So that's why the octave is so important that we actually give it the same note name. A, A2, A3. Another interval that's very important in almost all human musics is the fifth. 1, 2, 3, 4, 5. 1, 5. That's a fifth. That's also almost universally considered harmonious. In this case, some of the harmonics overlap, and the ones that don't are sufficiently far apart that they don't clash. In this case, we've got a ratio of 1.5 to 1, 110, 165. Half of the harmonics overlap, and the others are sufficiently separate that they don't clash or interfere with each other. Well, that's got something to do with harmoniousness, but harmoniousness is actually a rather complicated subject because it involves not only physics, but also physiology and fashion. There's a lot of that on PhysClips, which gives you an introduction, and also on our Music Acoustics website, so I'll leave that for you to investigate here for those who are interested. We've looked a little bit at string instruments. It's now time to think about the voice and wind instruments. There's something special about the human voice considered as a musical instrument, and it's this. If I were to sing a low note, 100 hertz, to produce that with a musical instrument, I would need a pipe that is this long. 100 hertz. 100 hertz. But it's obvious looking at me that my vocal tract isn't that long. My vocal tract, in fact, is 17 centimeters long, and that produces a much higher frequency. I can excite it various ways. It's round about 500 hertz, round about the B above middle C. And yet that's a note that's too high for me to sing. So we have this rather peculiar thing that the pipe here is far too short. I've got a trombone range instrument with a piccolo length pipe to interact with. This tells us that at least for male voices, the frequency of the voice is not governed by the length of the pipe, as we'll see that it is in most musical wind instruments. Well, musical wind instruments usually involve a standing wave in a pipe that reflects at either ends. I've mentioned already that it's rather important whether the pipe is open or nearly closed. Let's leave the description of that to this little video that we also made from PhysClips. Pipes have resonances that we can excite in different ways. Let's picture the reflection of a pressure pulse. At a closed end, the air can't move, so the compression pulse can only move back along the pipe. So the pressure wave is reflected with a phase change of 0. At a closed end, the displacement must be 0, so the displacement wave has a phase change of pi. At an open end, things are different. Here, the pressure is approximately fixed at atmospheric, so the sound pressure is approximately 0. So the pressure wave is reflected with a phase change of pi. The displacement is free, so the displacement wave has a phase change of 0. Let's look at sine waves in pipes. A flute is approximately cylindrical and open at both ends. Let's keep all the keys closed, so we have a pipe about 60 centimeters long, open to the atmosphere at both ends. So we have pressure nodes at both ends and displacement antinodes at both ends. The longest possible wavelength is twice the length of the pipe, so the lowest note is about C4, middle C, and the allowed mode diagrams look like this. A clarinet, on the other hand, is open to the air at one end, but not at the other. At the mouthpiece, it is almost closed, and near the vibrating reed, there's a pressure antinode. So the allowed mode diagrams for a clarinet look like this. Because of the bell, a clarinet is not cylindrical, so I'll put the clarinet mouthpiece on the flute body. This new instrument plays an octave lower than the flute, and its even-numbered resonances are missing. A question for you. Which is more important to the sound, the body or the mouthpiece? And why? So there's an introduction to vibration, sound, musical string instruments and musical wind instruments. That's as far as we'll go in the syllabus of this little subject, but of course there's a lot more interesting things to discover. As Liz mentioned when she was introducing me, my research lab researches the acoustics of the voice and musical instruments and the ear, and so we have a large website with many pages of introductory material on different musical instruments and the voice and hearing. The other site that I've been referring to regularly, and from which all of the film clips and the animations have come in this series of lectures, has been PhysClips. If you want to chase some of these topics further at the level of a first-year university course, then PhysClips is a good place to go. Here are some starting points.
Special thanks to Sebastian Frick for doing all the filming and editing of this video. If you'd like to find out more about sound or the voice, then it would be a good idea to visit these PhysClips sites. A webpage about the music group at UNSW can be found at this final address if you are interested in finding out more about this topic.